Hi, I'm Jennifer Neville. Thank you for joining me for my talk here at the Microsoft Research Summit. I'm a senior principal researcher in the Productivity and Intelligence Group at Microsoft Research in Redmond. And today I'm going to talk about extracting pragmatics from content interactions to improve search and recommendation in the enterprise. So the goal of this work is really to develop machine learning methods for graphs that will help move us towards more effective personalized search and recommendation systems for searching over things like your personal web or searching over the various modalities of information that you have in an enterprise system. And the motivation for using graphs in this space is that often in these more personalized settings, the search data that's available to learn how to do search and recommendation is often limited in terms of the number of interactions with the system as well as the content available to use for the machine learning methods. It's more limited compared to traditional web search. And the key idea that we have in this work is that in this sparse data regime that we often have, we do have very rich interaction data between people and the content. So we have information about meetings that you're attending and some content about the reason for that meeting. We have emails that go between people. We have documents that you've written and shared with people. And all of that relational information can be a way to offset the data sparsity that we have with respect to traditional search systems. And the reason for that this rich data can offset that sparsity of content is that the interactions between people and content provide what we're referring to as a source of linguistic pragmatics. And that means that the social interactions among the people and with the content are really cues to the meaning of that content, which can be used to enhance the semantic understanding that we would get from applying traditional NLP-based methods. And so for motivation to show this, I'm going to talk quickly about the use of the Bing navigation graph. I should have mentioned that I'm going to talk about work that has been done by people throughout Microsoft Research. So sometimes at the bottom you'll see references to papers where you can go find more information. So this, the graph on the right-hand side of the screen here is a graph of a visualization of part of the Bing navigation graph where we have connections between queries that people do based on how they navigate through those queries in the web pages. And the coloring of this graph indicates topics of content that cluster naturally together based on this navigation structure. And what this shows is that even without access to the content at all, the structure of the graph and how people move through this content and use the content really can reveal some of the semantic structure very clearly. And as an example of that, this interaction content can be used to identify communities of topics or web pages that cluster together in this interaction graph, which can be used to improve search recommendations. And so here's a zoom into part of that graph that I showed you before, where there's information about different cars and how people search over them. And you can see here that some of the cars, like the Maserati and the Bentley, cluster together, meaning that people tend to search for them at the same time or in sequence in different sessions, compared to including that with, say, a Buick or a Pontiac. And so this type of information that we would glean from these communities can be used to improve search recommendations, particularly to help people discover different parts of the web that they might not have been searching for before. And so this is just a very quick example to show you how we don't even need to know the content of the pages in order to extract some of the semantic information about which topics or which products are most likely to be searched together. So the users and how they interact with that content is providing the information for us. And so that's really a motivation to move towards a whole direction of research that focuses on incorporating both the graph structure and the content itself into representation learning in graph neural networks. And the sort of technical direction that we have to move to develop these methods is really to move beyond the traditional GNN type formulations that focus primarily on using the relational structure to improve predictions in the graph based on a relatively small number of node features. So these may be attributes of users or pages that are in the graph. And instead, when we move to trying to incorporate content, there's a much broader set of information that we have to include into those structures. And the signals that the content can provide are along a number of different dimensions in the graph neural networks, and so you'll see this in the research that I present in a second. But what the content can do is amplify the data signal that you have available if that data signal is sparse, because we can propagate information from long-range neighbors to offset the data sparsity. It also can incorporate a wider variety of relational structure, incorporating heterogeneous links between, say, the users and the documents that they access or the noun phrases that they use. And also the content itself provides a means to moderate the relational signal that we observe between users. So for example, the content of the email that you send to one of your colleagues can provide some context as to the type or strength of that relation. And so these are the types of things that we're trying to incorporate into the models in order to improve their ability to be used for search and recommendation tasks. So what I'll talk about quickly is just a few different snippets of research that can give you a sense of the potential for moving in this direction. And so the first research I'll talk about is using these types of ideas in search within your own personal web. And the goal here is to help people better organize and search over their own personal information based on how they interact with that information while they're working. And so the personal web is really a construct that's very much like the larger World Wide Web, but focused on all the things that you do inside your own computer as you're working with documents that you're editing or creating, sending to people, writing emails, attending meetings, and searching for things on the web. All of these things provide information about what you're working on and how important it is to the task that you're working on right now. And so the goal here then is to learn from these traces of activity of how you transition from task to task throughout the day, and use that structure to make better recommendations for what content you might need at a particular time. So for example, if you're making a presentation, you might need some updated information from an email that you just got from a relevant colleague, or you might need some a graphic from a Word document that you had created earlier. And so anticipating these kind of connections allows us to make better recommendations and improve people's productivity. And so in this case, what we want to do to automatically make those recommendations is to use the graph connections that would occur from the activity that you're involved in day to day to extract these pragmatic signals that I talked about before, because the way you interact with your data over the course of your workday provides a lot of semantic meaning as to what's the importance or the impact of that information. And so just a quick view of what the model looks like in this case. What we want to do is construct this graph from your personal corpus and how you interact with the various documents and artifacts over time, and represent those as feature-based documents based on the noun phrases or the topics that you have in those various aspects of content, and then propagate the representations that we learn throughout the graph, taking into account those attributes as well. And so the idea here is that we're going to learn a representation of the documents themselves, but also try to propagate and smooth those representations across the graph of activity so that the representations of things that you often use a lot together end up being similar. And so that would mean that web pages, for example, that you access at the same time as you make certain documents, that their representations in space in latent space should be similar, so that when we go to make recommendations, we'll be able to use that representation to make more effective recommendations. And so given this kind of structure, we can look at how we do in terms of prediction of which items are related to other items over your use in the day. And when we do this kind of content plus graph propagation type of representation, we do a much better job of identifying items with strong relationships. So that's the set of results on the bottom of this graph. Okay, so a second project that I wanted to talk about is using the behavioral interactions in the graph with the content to improve enterprise search and recommendation. So this is moving from the personal web search and recommendation to now enterprise search and recommendation. And in this case, what we want to do is consider the larger enterprise graph and how people interact with each other and with documents over time. And so here on the right, I'm showing you a simplification of the graph where we just have people writing and sharing and editing documents in the middle. And we have content that we've extracted from those documents in terms of topics or key phrases. And what we want to do here is look at the larger activity structure across the enterprise to again extract this pragmatic context, the pragmatic signal about what's the meaning of the information in each of those documents based on how people interact and use those documents. And what we'll do is use these enterprise patterns to improve the local recommendations we'd use for a particular user. And in this case, the privacy model is that we're not pushing information from other people in the enterprise to the user. We're still going to do recommendations over only what the user can see, but these larger pragmatic patterns that we're learning from the enterprise will be pushed down to re-rank the importance of the content that a user sees locally. And so an example of that is using this graph to, for example, predict which topics or projects a user is involved in. We could predict which documents are relevant to a particular topic or which documents to surface to the user and recommend to the user. And in this case, what we're trying to do is look again at collective inference over this larger enterprise graph compared to a conventional NLP baseline that uses more local information about the content. And so here is one illustration of this with respect to predicting which topics or projects a person is working on. If we consider just the user's information in isolation, just their content in isolation, we have an intern here on the left and a mentor on the right. And so you might see some topics that are extracted for the mentor. You can see a lot of those are acronyms that probably correspond to projects that mentor is working on. But the intern, because they have less information, they've just started there, you can see that the kind of topics that are extracted are things like events, like an intern event or a morning coffee. And so those are probably those are less relevant, and we would like to find more relevant topics or projects that are not as present in their content. But if we start to look at the graph structure of how they talk to each other, we can see that there's messages and emails and meetings that in documents that are propagated or jointly involve both the intern and the mentor, but also their colleagues in their larger group. And once we start to use this link structure, we can re-rank the topics, and we can find that the sort of spurious events that come up in the intern's ranking because of lack of textual content get pushed down, and the other topical, the other topics are pushed up because of their importance in the larger group structure that this intern is a part of. And so the intuition here is that because people that work together work on similar topics, then using this larger graph is going to do a better job of helping us deal with cases where there's sparse textual data. And to give you some indication of the potential of using this graph plus content information to improve recommendations, here are some relative performance results where we see the graph model provides significant gains in precision and recall compared to previous NLP-based baseline approaches. And this is these are some numbers over a large subset of the Microsoft graph that we were using to do this analysis, where we had, you can see millions of topics and users, user topic edges, and we're trying to predict which topics are associated with which users. And so these results, again, show how the content plus graph representation can improve the ability for us to predict which topics each user is working on. And we also have recent work showing that there's similar gains for predicting related people, related topics, and related documents. Okay, so the last project that I wanted to talk about was moving towards personalization for a user based on their social context. And so in this case, what we wanted to do is use the conversational content from across the communications between users to moderate the information that we see in each of the links, and use that to do a better job of link prediction in social contexts. And so this is external work that I did with one of my students at Purdue. And in this case, our goal was to learn edge representations in cases where we had really rich heterogeneous structure in the data, where we have multiple kinds of relations that each pair of users is part of, and we also have these directed messages that go back and forth between users, and we wanted to incorporate this textual content on the messages going back and forth to identify the social signals in their relationships to improve the predictions that we would make. And so the basic idea is we're going to learn these low-rank relational projection matrices for each of the different relations that users can be part of, and that will predict whether or not they have a relation in that particular type of view or not. Okay, so the key idea in this architecture that I wanted to talk about is these conversational-based factors that we're going to use to capture the strength and affinity of relationships between users. When we see textual messages going back and forth between two users, we don't know what they're talking about and how it corresponds to each of the different relations we'd see across those edges. And so this is our current effort at trying to capture that meaning. And what we do to construct these factors is we take all the pairs of nodes that are involved in a particular relation, and then we create a dictionary of the words that are used primarily amongst those pairs. And then we do that for each of the relations that we have. And so we build up a TF-IDF-like dictionary for each relation, and then we can calculate the conversational similarity factor and the conversation frequency factor of a particular interaction between a pair of users with respect to these dictionaries. So a higher value of the similarity factor means that two users are discussing things that tend to be discussed by people in that particular relation or view here, and a higher conversation frequency factor indicates that they have a stronger interaction with respect to that view. And then once we have these scores, we can use them in a larger embedding framework that I won't go into a lot of the details about, but what we have is we're learning a joint model of the representations across the different relations, And we do that by having a shared node embedding, but we have these separate low rank projections for each of the relations that we're learning over. And then we have each of the views is moderated by these conversational factors. So we can learn a single global edge representation as well as a representation for each type of edge or each relation independently. And so when we learn this larger joint model, we can use it to apply the model for link prediction across the various types of relations that we have. And what we've found is that using these conversational factors with our model, which we call Merle, helps us to significantly improve prediction performance across all of the views. And really the reason for that is that the joint views is allowing us to share the information and the text and the relations across all different types of prediction tasks, but the low rank projections and the conversation factors tell us which dimension is more important for which pairs. So we are simultaneously using the joint information well at the same time, but what we need to do is to be able to say which dimension it's more important for. And we've used similar ideas to this to improve node prediction as well as link prediction. So these conversation factors are really a way to leverage the textual content or the conversation that goes back and forth between users, even if you don't know why they're having those conversations. So in conclusion, I just talked about a few different types of recent research recently to show you that these graph learning, machine learning, and AI systems are really uniquely positioned to be able to learn with these social pragmatics or linguistic pragmatics that take into account the data trails of how people interact with each other and with content across multiple modalities of interaction data. So this could be chats in Teams, it could be information in email, it could be comments in documents. And in this way, we think that graph learning methods are going to be able to move beyond traditional NLP-based methods, particularly in these sparse data regimes where there's a long tail of information with sparse text. And in that case, the graph is going to provide a really helpful means to improve search and recommendation in these personalized settings. And that the larger organization provides a way to a new source of information, but that we can learn over that in a privacy compliant manner. And so really the technical research directions to push in this, to push towards this involve graph learning, as I was talking about today, but also focus on public-private learning across these levels of information, both personalized individuals as well as organizational. And we need to move towards real-time in situ recommendations and think about social reinforcement learning methods to make decisions on the fly in a sequential setting. So with that, I will say thank you.